Look at your hand. Right now, as you watch this, your body is being held together by electromagnetic forces between atoms. Those forces prevent your molecules from collapsing into a point of infinite density. But there are places in the universe where those forces mean nothing, where matter stops obeying the rules, where the fabric of space-time itself tears open and everything, light, matter, information, falls into a geometric wound that cannot heal. Black holes are not cosmic vacuum cleaners. They are execution chambers, where the laws of physics go to die. Scientists have discovered that black holes come in varieties, not just different sizes, but fundamentally different species of gravitational predators, each one breaking reality in its own unique way. Some formed from the deaths of massive stars. Others appeared before stars even existed. Some wander alone through the void. Others hunt in pairs, orbiting each other in a death spiral that sends ripples through the fabric of space itself. And the most terrifying ones might be forming right now in laboratory particle accelerators, or emerging from the quantum foam that underlies all existence. What you are about to hear is not speculation. Every type of black hole I will describe has either been directly observed, detected through gravitational waves, or exists as an inevitable mathematical consequence of Einstein's equations. The universe has created gravitational monsters in at least 9 distinct configurations, and each one represents a different pathway to cosmic annihilation. The smallest ones could fit inside an atom but contain the mass of a mountain. The largest ones are billions of times more massive than our Sun, sitting at the centers of galaxies like malevolent engines that have been feeding for 13 billion years. Some rotate so fast, they drag space-time around them like water circling a drain. Others carry electric charges that create magnetic fields powerful enough to accelerate particles to near light speed. And theoretical physics suggests that even stranger varieties might exist in the quantum realm or hidden in higher dimensions we cannot perceive. By the time this video ends, you will understand that black holes are not one phenomenon. They are a taxonomy of cosmic predators, each species adapted to destroy matter in increasingly exotic ways. You will learn the precise mechanisms by which each type forms, how they feed, how they die, and what happens to anything unlucky enough to cross their event horizons. And you will discover that the universe is far more inventive at creating gravitational nightmares than anyone imagined. The journey begins with the type of black hole that spawned all our fears. The stellar mass black hole, born from the violent death of massive stars. And it represents the most common form of these cosmic execution chambers. But as you will soon discover, stellar black holes are merely the beginning of a hierarchy of gravitational monsters that extends from objects smaller than atoms to structures that dwarf our entire solar system. If you are ready to understand every mechanism by which the universe creates these wounds in space-time, stay watching. Because what comes next will change how you see the darkness between stars forever. The universe manufactures approximately 100 million stellar mass black holes every year. Right now, as you hear this, somewhere in the observable cosmos, a massive star has just exhausted its nuclear fuel and begun the process of collapsing into a gravitational singularity. The collapse takes less than 1 second. In that single second, a sphere of matter larger than Earth compresses into a point of infinite density, and another execution chamber opens in the fabric of space-time. Stellar mass black holes are the most common type of black hole in the universe, and they represent the standard pathway by which normal stars become cosmic predators. These objects contain between 3 and 100 solar masses, compressed into regions smaller than most cities. They form through a process so violent that it releases more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. And there are an estimated 100 million of them scattered throughout our galaxy alone, invisible gravity wells waiting for matter to stumble into their grasp. The birth of a stellar mass black hole begins long before the actual collapse. It starts with a star at least 25 times more massive than our Sun, These stellar giants burn through their nuclear fuel at astonishing rates, fusing hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each fusion reaction releases energy that creates an outward pressure holding the star against its own crushing gravity. But iron is different. Iron is the endpoint. When you fuse iron, you do not get energy out, you consume energy. The stellar core becomes a ticking time bomb of iron ash, growing heavier with each passing moment, held up only by the degeneracy pressure of electrons refusing to occupy the same quantum state. Then the core reaches a critical mass, 1.4 solar masses, a threshold discovered by Indian astrophysicist Subrahmanyan Chandrasekhar in 1930. At this boundary, electron degeneracy pressure fails. The electrons get forced into the atomic nuclei, combining with protons to form neutrons. In a fraction of a second, the core collapses. The outer layers, suddenly unsupported, fall inward at nearly 1/4 the speed of light. What happens next is called a core collapse supernova. The infalling matter slams into the incompressible neutron core and rebounds, creating a shock wave that tears through the star. The explosion is so energetic that it outshines the entire galaxy that hosts it. For a few weeks, a single dying star emits more light than 200 billion normal stars combined. The blast wave carries away 99% of the star's mass, scattering it into space. Heavy elements forged in the final moments, gold, platinum, uranium, get distributed across light years of space, seeding future generations of stars and planets. But the core remains. If that core contains more than approximately 3 solar masses, not even neutron degeneracy pressure can save it. There is no known force in physics that can halt the collapse. The matter continues shrinking, past the size of Earth, past the size of a city, past the size of a mountain, until it vanishes into a geometric point of zero volume and infinite density. A singularity forms, and space-time warps so severely around it that an event horizon crystallizes into existence. A one-way membrane that defines the boundary beyond which escape becomes mathematically impossible. The event horizon of a stellar mass black hole is deceptively small. A black hole with 10 solar masses has an event horizon with a radius of just 30 kilometers. You could fly from New York to Los Angeles in 5 minutes at that distance. But compressed into that small sphere is a mass 10 times greater than the Sun, creating a gravitational field so intense that even light moving at 300 million meters per second cannot escape. Cygnus X1 was the first stellar mass black hole ever discovered, and its identification represents one of the most important confirmations in astrophysics history. Located approximately 6,000 light-years from Earth in the constellation Cygnus, this system caught astronomers' attention in 1964 when early X-ray telescopes detected powerful X-ray emissions coming from that region of sky. But X-rays do not come from black holes directly. They come from the matter being destroyed just before it crosses the event horizon. Cygnus X1 is a binary system. The black hole, which contains approximately 21 solar masses, orbits a blue supergiant star designated HDE 226868. The black hole's gravity tears material away from its companion star, creating an accretion disk of superheated gas spiraling inward. As this gas falls toward the event horizon, gravitational forces compress it and heat it to temperatures exceeding 10 million degrees Kelvin. At these temperatures, matter emits primarily in X-rays. The accretion disk becomes a cosmic furnace, converting gravitational potential energy into radiation with terrifying efficiency. The confirmation that Cygnus X1 contained a black hole required careful observation and deduction. Astronomers measured the orbital period of the binary system and the velocity of the visible star. Using Kepler's laws, they calculated that the invisible companion had to contain at least 8 solar masses, later refined to 21 solar masses through more precise measurements. This mass exceeded the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can possess, before collapsing into a black hole. The limit sits at approximately 3 solar masses, though the exact value depends on the equation of state for ultra-dense matter. Anything heavier cannot be a neutron star. It must be a black hole. Stephen Hawking famously made a bet with physicist Kip Thorne in 1975 that Cygnus X1 did not contain a black hole. Hawking later conceded the bet in 1990, acknowledging that the evidence had become overwhelming. The concession marked a turning point in astrophysics. Black holes transitioned from mathematical curiosities to confirmed physical objects that existed in detectable numbers throughout the galaxy. Since Cygnus X1, astronomers have identified dozens of stellar mass black holes through X-ray observations of binary systems. Each discovery follows the same pattern. Intense X-ray emissions. An invisible, massive companion. Orbital dynamics that demand masses exceeding the neutron star limit. But these X-ray bright systems represent only a small fraction of the total population. Most stellar mass black holes drift alone through space, isolated remnants of stars that died millions or billions of years ago. These solitary black holes emit no light. They accrete no matter. They are invisible predators detectable only through their gravitational influence on nearby objects. Astronomers estimate that the Milky Way galaxy contains approximately 100 million stellar mass black holes based on stellar evolution models and supernova rates. Every star more massive than 25 solar masses will eventually create a black hole. Our galaxy forms roughly 7 new stars every year, and approximately 0.1% of those stars are massive enough to end as black holes. Over the galaxy's 13 billion-year history, this adds up to an enormous population of stellar remnants that we cannot see directly. The detection of isolated stellar mass black holes requires gravitational microlensing, a technique that exploits general relativity's prediction that massive objects bend light. When a black hole passes between Earth and a more distant star, the black hole's gravity acts as a lens, temporarily magnifying the background star's light. By measuring the duration and intensity of this magnification event, astronomers can calculate the mass of the lensing object. If that mass exceeds 3 solar masses but produces no light, it must be a black hole. In June of 2022, astronomers announced the discovery of the closest known stellar mass black hole to Earth. The object, designated Gaia BH1, sits approximately 1,600 light-years away in the constellation Ophiuchus. It contains roughly 10 solar masses and orbits a Sun-like star with a period of 185 days. The black hole was discovered through precise measurements of the companion star's motion, which revealed the gravitational influence of an invisible massive object. Gaia BH1 represents a significant find because it demonstrates that stellar mass black holes can exist in relatively wide orbits with normal stars, creating systems stable enough to survive for billions of years. But not all stellar mass black holes are created equal. The mass range from 3 to 100 solar masses creates dramatic differences in behavior and characteristics. The smallest stellar mass black holes, hovering just above the 3 solar mass threshold, have event horizons barely 20 kilometers across. These compact objects create extreme tidal forces. An astronaut falling toward a 3 solar mass black hole would experience spaghettification, the stretching of matter into thin streams, while still several thousand kilometers from the event horizon. The difference in gravitational pull between their head and feet would become so severe that molecular bonds would rupture, reducing any structure to a stream of individual atoms. Larger stellar mass black holes, approaching 100 solar masses, create much gentler tidal forces near their event horizons. The event horizon radius scales linearly with mass, so a 100 solar mass black hole has an event horizon approximately 300 kilometers in radius. An astronaut could cross this event horizon without immediate physical disruption, not realizing they had passed the point of no return until attempting to turn around. The tidal forces would remain survivable for hours during the fall toward the singularity, though the astronaut would experience increasingly severe time dilation effects as perceived from the outside universe. The most massive stellar mass black holes challenge our understanding of stellar evolution, Theoretical models suggest that stars more massive than approximately 150 solar masses should not produce black holes at all. These stellar giants create such powerful radiation pressure that they blow themselves apart in pair instability supernovae before their cores can collapse. The energy becomes so intense that it creates particle-antiparticle pairs, gamma rays converting into electrons and positrons. This pair production absorbs energy from the core, causing it to contract, which increases temperature and pressure, which accelerates pair production in a runaway feedback loop. The result is a complete disruption of the star with no remnant left behind. Yet observations have detected stellar mass black holes with masses approaching 100 solar masses, pushing the boundaries of what stellar evolution models predict. The most famous example came from gravitational wave astronomy. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO for short, detected ripples in spacetime produced by the merger of two black holes. The signal, designated GW150914, revealed that black holes with masses of 36 and 29 solar masses had collided, producing a final black hole of 62 solar masses. 3 solar masses worth of energy radiated away as gravitational waves, creating a signal detectable across more than 1 billion light-years of space. The existence of 36 and 29 solar mass black holes surprised many astrophysicists. Stars massive enough to produce black holes in this mass range should arguably undergo pair instability supernovae. The detection suggests either that stellar evolution models are incomplete, or that these black holes formed through exotic channels. Perhaps they represent the merger products of earlier generations of black hole collisions, black holes cannibalizing other black holes to reach masses that direct stellar collapse cannot achieve. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of stellar mass black hole mergers. Each detection provides data about the population of black holes in the universe, their mass distribution, their spin rates, and their orbital characteristics. The gravitational wave signals encode information about the final seconds before merger. When the two event horizons spiral together at appreciable fractions of light speed, warping spacetime so severely that the waves propagate across cosmic distances as permanent ripples. The spin of stellar mass black holes adds another dimension to their diversity. When a massive star collapses, conservation of angular momentum guarantees that the resulting black hole will rotate. The rotation rate depends on the star's initial spin and on mass loss during evolution, but most stellar mass black holes are expected to spin at significant fractions of their maximum possible rotation rate. A rotating black hole is fundamentally different from a non-rotating one. The rotation drags spacetime around the black hole in a phenomenon called frame dragging. Near the event horizon, space itself is pulled in the direction of rotation so strongly that nothing, not even light, can resist the motion. This region is called the ergosphere. The fastest spinning stellar mass black hole ever observed sits in the system GRS 1915 plus 105, located approximately 40,000 light-years from Earth. X-ray observations indicate that this black hole rotates at very close to the maximum rate allowed by general relativity, spinning so fast that its event horizon is significantly oblate. Bulging at the equator and flattened at the poles, the spin rate approaches the theoretical limit where the event horizon would vanish and the singularity would become naked, exposed to the outside universe. This limit, called the Kerr bound, prevents singularities from being visible, preserving what physicist Roger Penrose called cosmic censorship, the idea that nature forbids naked singularities. Stellar mass black holes also exist in exotic binary configurations. Some orbit other stellar mass black holes, creating systems where two event horizons dance around each other, destined to eventually spiral inward and merge in cataclysmic collisions that release more energy in a fraction of a second than all the stars in the observable universe emit during the same time period. Others orbit neutron stars, creating mixed binaries where a black hole slowly consumes its ultra-dense companion. Still others orbit normal stars, as in Cygnus X1, gradually draining their companions and converting stellar matter into radiation with greater efficiency than any nuclear reaction. The feeding behavior of stellar mass black holes follows predictable patterns determined by accretion physics. When matter falls toward a black hole, it does not fall straight in. Conservation of angular momentum forces the infalling material into an accretion disk, a flattened structure where gas orbits the black hole at increasing speeds as it spirals inward. The inner edge of the accretion disk reaches temperatures of tens of millions of degrees, hot enough to emit X-rays. But the efficiency of this process is limited. Only a small fraction of the infalling matter's rest mass energy converts to radiation. Most of the mass crosses the event horizon and vanishes into the singularity, adding to the black hole's mass and causing its event horizon to grow. A stellar mass black hole accreting matter at typical rates will double its mass in approximately 100 million years. This seems slow on human timescales, but represents rapid growth on cosmic timescales. Over billions of years, a 10 solar mass black hole could theoretically grow to 100 solar masses if it had access to sufficient fuel. But most stellar mass black holes exist in environments where fuel is scarce. The space between stars contains very little matter. Even in binary systems, the rate at which a black hole can tear material from its companion is limited by the companion's structure and the orbital separation. Most stellar mass black holes will never grow beyond their birth masses by more than a few percent. The depth of stellar mass black holes remains theoretical because the timescales involved dwarf the current age of the universe. Stephen Hawking demonstrated in 1974 that black holes should emit thermal radiation due to quantum effects near the event horizon. Virtual particle pairs that spontaneously form in the vacuum can be separated by the extreme tidal forces near a black hole, with one particle falling in while the other escapes. This process, called Hawking radiation, causes black holes to slowly lose mass. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A 10 solar mass black hole has a temperature of approximately 6 billionths of a degree above absolute zero, far colder than the cosmic microwave background. Such a black hole will actually gain mass by absorbing background radiation faster than it evaporates through Hawking radiation. Only after the universe expands and cools significantly will stellar mass black holes begin to shrink. The evaporation time for a 10 solar mass black hole is approximately 10 to the power of 67 years, a number so large it makes the current age of the universe, 13.8 billion years, seem like an eye blink. As the black hole evaporates, its temperature increases, causing it to radiate faster. The process accelerates exponentially. In the final second of a black hole's life, it releases more energy than it emitted during all previous eons combined, exploding in a flash that would momentarily outshine nearby stars. But this finale lies so far in the future that it belongs to an epoch when stars no longer exist, when galaxies have evaporated, when the universe has entered its final twilight. Stellar mass black holes represent the universe's standard mechanism for creating gravitational singularities. They form through a well-understood process. They exist in observable numbers. They follow predictable evolutionary paths, but they are merely one species in a taxonomy of gravitational monsters that extends to scales both far smaller and incomprehensibly larger. The cosmic execution chambers come in varieties that challenge intuition and push the limits of physical law. At the center of our galaxy, 26,000 light-years from Earth, sits a gravitational monster 4 million times more massive than the Sun. Its event horizon stretches 17 times the distance from the Sun to Neptune, creating a spherical region of no escape larger than our entire solar system. This object is called Sagittarius A star, and it has been feeding at the core of the Milky Way for billions of years, growing more massive with each galaxy that falls into its grasp. It is not an anomaly. Every large galaxy in the observable universe harbors a supermassive black hole at its center, and these cosmic engines have shaped the structure of the universe on the largest scales. Supermassive black holes contain between 100,000 and tens of billions of solar masses. They occupy a mass range so extreme that a single supermassive black hole can outweigh entire globular clusters. containing millions of stars. The largest known supermassive black hole, designated TON 618, sits at the center of a quasar 10 billion light-years away and contains approximately 66 billion solar masses. Its event horizon has a radius of 1,300 astronomical units, meaning light would take more than 7 days to cross from one side to the other. This single object is more massive than some small galaxies. The existence of supermassive black holes creates an immediate problem for astrophysics. Stellar mass black holes form from collapsing stars through a well-understood process, but no star can create a supermassive black hole directly. Even the most massive stars produce black holes no larger than 100 solar masses. To reach millions or billions of solar masses requires accumulating matter over time. The question that has haunted cosmologists for decades is simple and terrifying. How did these monsters grow so large so quickly? The universe is 13.8 billion years old. Astronomers have discovered supermassive black holes containing billions of solar masses, existing when the universe was less than 1 billion years old. These objects appear in quasars from the early universe, blazing beacons powered by black holes that somehow achieved billions of solar masses in a fraction of the universe's current age. The timescale problem is severe. A black hole accreting matter at the maximum possible rate, called the Eddington limit, would still require hundreds of millions of years to grow from stellar mass to supermassive scales. Yet these ancient, supermassive black holes existed when the universe was too young for such prolonged growth. Several theories attempt to explain this impossible growth. The first proposes that supermassive black holes formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. In this scenario, clouds containing 100,000 or more solar masses of gas collapsed directly into black holes, giving them a massive head start. These seed black holes could then grow to supermassive scales through normal accretion within the available time. But direct collapse requires very specific conditions. The gas must be metal-poor, hot enough to prevent fragmentation into stars but cool enough to collapse gravitationally. Such conditions may have been rare in the early universe. The second theory suggests that supermassive black holes grew from runaway collisions in dense star clusters. In the cores of the first galaxies, where stellar densities were extreme, massive stars could collide and merge repeatedly, creating progressively larger objects that eventually collapsed into intermediate mass black holes. These intermediate seeds could then grow through accretion to supermassive scales. Computer simulations show this process can work, but it requires initial stellar densities far higher than observed in modern galaxies. The third and most disturbing theory proposes that supermassive black holes are primordial objects that formed in the first seconds after the Big Bang through quantum fluctuations in the primordial density field. These primordial black holes would have been present from the universe's beginning, sitting in dark matter halos like gravitational spiders waiting for gas to fall into their webs. As galaxies formed around them, they would feed and grow, reaching supermassive scales while their host galaxies were still assembling. This theory has the advantage of explaining why every large galaxy contains a supermassive black hole, but it requires exotic physics in the early universe that remains unproven. Regardless of their formation mechanism, supermassive black holes have profoundly influenced galactic evolution. The mass of a galaxy's central supermassive black hole correlates tightly with properties of the galaxy's bulge. The dense central region of stars. Galaxies with massive bulges contain more massive black holes, following a relationship discovered by astronomers in the late 1990s. The correlation is so precise that you can predict a black hole's mass to within a factor of 3 just by measuring the velocity dispersion of stars in the galactic bulge. This relationship implies a deep connection between black hole growth and galaxy formation, as if the two processes are locked together through feedback mechanisms we are still working to understand. The feedback operates through radiation and outflows from the accretion disk. When a supermassive black hole feeds actively, it becomes a quasar, an active galactic nucleus that can outshine the entire host galaxy. The accretion disk around an actively feeding supermassive black hole converts gravitational potential energy into radiation with 20 to 30% efficiency, far exceeding the 0.7% efficiency of nuclear fusion. A supermassive black hole accreting just one solar mass of material per year releases more energy than 10 trillion suns. This energy doesn't just radiate away harmlessly. It heats gas in the surrounding galaxy, driving powerful winds that can reach velocities of thousands of kilometers per second. These galactic-scale outflows sweep away the cold gas needed for star formation, quenching star birth across the entire galaxy. The supermassive black hole, despite containing less than 1% of the galaxy's total mass, can regulate star formation in a region millions of light-years across. This feedback prevents galaxies from converting all their gas into stars and explains why massive galaxies tend to be red and dead, filled with old stars but forming few new ones. Sagittarius A star, the supermassive black hole at the center of the Milky Way, has been directly imaged through radio interferometry. In May of 2022, the Event Horizon Telescope collaboration released an image showing the black hole's shadow, a dark circular region surrounded by a bright ring of emission from the accretion disk. The image confirmed predictions from general relativity about the appearance of black hole event horizons and provided direct visual evidence that Sagittarius A star is indeed a black hole rather than some alternative compact object. The Event Horizon Telescope is not a single instrument but a network of radio telescopes scattered across the globe, from Chile to Hawaii to the South Pole. By combining data from these widely separated telescopes using a technique called very long baseline interferometry, astronomers created a virtual telescope the size of Earth, achieving angular resolution fine enough to resolve the event horizon of Sagittarius A star despite its distance of 26,000 light-years. The resulting image shows a ring of emission approximately 52 micro-arcseconds in diameter, matching the predicted size of the black hole's photon sphere, the region where light orbits the black hole before either escaping or falling in. Sagittarius A star is currently in a low-activity state, accreting only a tiny fraction of the Eddington limit. The accretion rate is approximately 10 to the power of -9 solar masses per year, meaning it would take 1 billion years to consume a single solar mass of material. This quiescence explains why the Milky Way's core appears relatively quiet compared to active galactic nuclei in other galaxies. But Sagittarius A star has not always been so docile. Evidence suggests it underwent violent feeding episodes in the past, including a major outburst approximately 6 million years ago that created giant gamma-ray bubbles, extending 25,000 light-years above and below the galactic plane. These Fermi bubbles, discovered by NASA's Fermi Gamma-Ray Space Telescope in 2010, testify to periods when our galaxy's central black hole fed actively and drove powerful outflows. The future holds another feeding episode. The Andromeda Galaxy is approaching the Milky Way at approximately 110 kilometers per second, and the two galaxies will collide in approximately 4 billion years. During the merger, the central supermassive black holes will spiral toward each other, eventually coalescing into a single black hole containing approximately 8 million solar masses. The merger will trigger intense star formation and feed both black holes with copious gas, potentially creating a bright quasar visible across the universe. But this event lies far enough in the future that the Sun will have already entered its red giant phase, making the galactic core cataclysm irrelevant to Earth's fate. The most massive supermassive black holes exist in the centers of giant elliptical galaxies and quasars. TON 618, with its 66 billion solar masses, powers one of the most luminous quasars in the universe, emitting energy equivalent to 140 trillion suns. The quasar's light has been traveling for 10 billion years to reach Earth, meaning we observe it as it appeared when the universe was only 3.8 billion years old. At that epoch, this monster had already grown to billions of solar masses through mechanisms that remain poorly understood. Even more massive black holes may exist but remain undetected because they reside in distant, faint galaxies where measurement uncertainties are large. The theoretical upper limit for supermassive black hole masses is approximately 50 billion solar masses, set by the Eddington limit and the available time for growth since the Big Bang. Black holes more massive than this threshold would have required sustained accretion at super-Eddington rates, which may be possible through specific accretion geometries but remains uncertain. Supermassive black holes spin at rates determined by their accretion history. If a black hole accretes matter primarily from a single accretion disk with consistent angular momentum, it will spin up toward the maximum rotation rate. If it grows through chaotic accretion or by merging with other black holes with random orientations, its spin will be lower. Observations suggest most supermassive black holes spin at moderate to high rates, with some approaching the theoretical maximum. The fastest spinning supermassive black hole, measured to date, sits in the galaxy NGC 1277, approximately 400 million light-years from Earth. X-ray observations indicate this black hole rotates at least 98% of the maximum possible rate, spinning so fast that its ergosphere extends far from the event horizon. The rapid rotation affects the geometry of spacetime around the black hole, creating regions where standing still becomes impossible. Anything within the ergosphere is forced to move in the direction of the black hole's rotation, dragged along by the spinning fabric of space itself. Supermassive black holes sometimes launch jets, narrow beams of plasma that extend for millions of light-years into intergalactic space. These relativistic jets form when magnetic fields threading the accretion disk become twisted by the black hole's rotation, creating a magnetic catapult that accelerates particles to 99.9% of light speed. The jets carry enormous amounts of energy away from the black hole, depositing it in the surrounding intergalactic medium and affecting the formation of structure across cosmic scales. The jet from the supermassive black hole in the galaxy M87 extends for 5,000 light-years and appears as a bright streak in radio images. M87 itself hosts a supermassive black hole containing 6.5 billion solar masses, and it was the first black hole ever imaged by the Event Horizon Telescope. The image, released in April 2019, showed a bright ring of emission with a dark shadow in the center, confirming that the object was indeed a black hole and matching predictions from general relativity with stunning precision. The existence of jets requires both rapid black hole spin and strong magnetic fields threading the accretion disk. The magnetic field lines anchored in the disk get wound up by the black hole's rotation until they form tightly twisted spirals that act like electromagnetic rails, accelerating charged particles outward along the rotation axis. The power available for launching jets comes from the rotational energy of the black hole itself, extracted through a process called the Blandford-Znajek mechanism. As the black hole spins down, it can convert up to 29% of its rest mass energy into jet power, making rotating supermassive black holes the most efficient engines in the universe for converting mass into directed energy. Supermassive black holes occasionally wander away from galactic centers through gravitational recoil during mergers. When two supermassive black holes merge, the gravitational waves they emit carry momentum. If the merger is asymmetric, with black holes of different masses or spins, the waves can carry more momentum in one direction than others, giving the merged black hole a kick velocity. Theoretical calculations suggest recoil velocities can exceed 5,000 kilometers per second, fast enough to eject the merged black hole from its host galaxy entirely. Several candidate recoiling supermassive black holes have been identified in distant galaxies through spectroscopic observations showing velocity offsets between the black hole and the surrounding galaxy. These objects represent supermassive black holes in the process of being ejected, destined to wander through intergalactic space as rogue gravitational predators unbound to any galaxy. The largest recoil velocities occur when two equal-mass black holes with specific spin orientations merge, creating maximum asymmetry in the gravitational wave emission. The population of supermassive black holes in the universe is enormous. Most galaxies contain at least one, and the total number of supermassive black holes in the observable universe exceeds 100 billion. Together, they represent a significant fraction of the universe's total mass budget, though still dwarfed by dark matter and regular matter in stars and gas. The combined mass of all supermassive black holes in the observable universe is approximately 10 to the power of 15 solar masses, equivalent to 1 million Milky Way galaxies. The death of supermassive black holes will occur through Hawking radiation, but the timescales involved are incomprehensible. A supermassive black hole containing 1 billion solar masses will take approximately 10 to the power of 96 years to evaporate completely. For comparison, the current age of the universe is 10 to the power of 10 years. The evaporation time exceeds the current age of the universe by a factor of 10 to the power of 86, a number so large that writing it in decimal notation would require 86 zeros. During this evaporation, the black hole will shrink slowly, its temperature rising as its mass decreases. Eventually, billions of trillions of years from now, the black hole will enter its final phase, radiating away its last kilograms of mass in a burst of high-energy particles. But this endpoint lies so far in the future that it belongs to an epoch when the stars have long since burned out. When galaxies have evaporated, when protons themselves may have decayed, and when the universe has entered its final era of darkness and cold. Supermassive black holes represent cosmic anchors around which galaxies form and evolve. They regulate star formation through feedback. They launch jets that affect structure formation across megaparsecs. They merge during galaxy collisions, sending gravitational waves rippling through space-time. And they will persist long after every star has died, sitting in the dark cores of dead galaxies like tombstones marking where life and light once flourished. But supermassive black holes are not the largest objects on the mass spectrum of gravitational monsters. That distinction belongs to a hypothetical class that pushes the very limits of what physics allows. There is a hole in the mass spectrum of black holes, a gap so conspicuous that astronomers spent decades arguing over whether it represented a real absence or merely an observational limitation. Between the largest stellar mass black holes at 100 solar masses and the smallest supermassive black holes at 100,000 solar masses lies a range where black holes should exist but remain stubbornly difficult to find. These missing objects are called intermediate mass black holes, and their scarcity creates a fundamental problem for understanding how supermassive black holes form and grow. Intermediate mass black holes occupy the mass range from 100 to 100,000 solar masses, bridging the gap between stellar remnants and galactic-scale monsters. For decades, they existed primarily as theoretical constructs, predicted by formation models but lacking definitive observational confirmation. The problem is straightforward. Intermediate mass black holes are too massive to form from single stellar collapse but too small to power the bright quasars that make supermassive black holes easy to detect. They hide in environments where detection requires indirect methods and careful analysis of subtle gravitational signatures. The formation pathways for intermediate mass black holes differ fundamentally from those of their smaller and larger cousins. Stellar mass black holes form from individual massive stars. Supermassive black holes likely form from the direct collapse of massive gas clouds or from primordial seeds in the early universe. But intermediate mass black holes require exotic formation channels that involve multiple objects interacting in dense environments. The leading theory proposes that intermediate mass black holes form in globular clusters through runaway collisions. Globular clusters are ancient stellar cities containing hundreds of thousands to millions of stars, packed into regions only a few dozen light-years across. In the dense cores of these clusters, stellar collision rates can become significant. When two massive stars collide, they merge into a single, more massive object. If this merged star collides with another star before it has time to evolve and explode, it grows larger still. Through repeated collisions, a runaway process can build stars with masses exceeding 1,000 solar masses, objects too massive to support themselves through any known physics. These collision products collapse directly into intermediate mass black holes, Computer simulations of globular cluster evolution show that this runaway process can occur, but the conditions must be precisely tuned. The cluster core must be dense enough for collisions to occur frequently, but not so dense that three-body interactions eject stars before they can merge. The initial stellar population must contain enough massive stars to serve as collision seeds. And the process must occur quickly, within the first few million years of the cluster's life, before massive stars evolve and explode as supernovae. These requirements are stringent, suggesting that not every globular cluster will form an intermediate mass black hole. Alternative formation scenarios invoke the direct collapse of massive gas clouds in metal-poor environments during the early universe. In regions where heavy elements are scarce, gas clouds can grow to larger masses before fragmenting into individual stars. Under specific conditions, these clouds containing thousands of solar masses can collapse directly into intermediate mass black holes without first forming stars. This direct collapse pathway avoids the need for runaway stellar collisions, but requires very particular environmental conditions that may have been rare even in the early universe. A third possibility suggests that intermediate mass black holes form from the repeated mergers of stellar mass black holes in dense stellar environments. In clusters where stellar mass black holes sink to the core through gravitational interactions, they can form binary systems that merge through gravitational wave emission. The merged black hole, now more massive, can capture another stellar mass black hole and merge again. Through successive mergers, the black hole can climb the mass ladder from tens of solar masses to hundreds or thousands of solar masses. Each merger releases gravitational waves detectable by instruments like LIGO and Virgo, providing potential signatures of this hierarchical growth process. The first strong evidence for intermediate mass black holes came from X-ray observations of ultraluminous X-ray sources, as objects that emit X-rays at luminosities exceeding the Eddington limit for stellar mass black holes. These sources appear in the disks and halos of galaxies, away from the central supermassive black holes that dominate galactic nuclei. Their X-ray luminosity suggests they are powered by black holes more massive than 100 solar masses, accreting matter from companion stars or gas clouds. One of the best-studied ultraluminous X-ray sources sits in the galaxy M82, approximately 12 million light-years from Earth. Designated M82X1, this source emits X-rays with a luminosity exceeding 100 times what a 10 solar mass black hole could produce at the Eddington limit. The brightness variability and spectral characteristics suggest the source contains a black hole with a mass between 200 and 800 solar masses, firmly in the intermediate mass range. The black hole appears to be accreting matter from a stellar companion, though the nature of that companion remains uncertain. Not all ultraluminous X-ray sources require intermediate mass black holes. Some can be explained by stellar mass black holes accreting at super-Eddington rates, where radiation pressure is overcome through specific accretion geometries. Distinguishing between these scenarios requires detailed modeling of the X-ray spectra and timing properties, and for many sources, the evidence remains ambiguous. But a subset of ultraluminous X-ray sources shows characteristics that strongly favor intermediate mass black holes over alternative explanations. The most compelling evidence for intermediate mass black holes comes from gravitational wave detections. On September 2, 2019, the LIGO and Virgo detectors recorded a gravitational wave signal designated GW190521. The signal came from the merger of two black holes with masses of 66 and 85 solar masses, producing a final black hole containing 142 solar masses. This detection marked the first direct observation of an intermediate mass black hole, confirming that such objects exist in nature. The progenitor black holes themselves raise questions. An 85 solar mass black hole sits in a problematic mass range called the pair instability gap. Stars that would produce black holes in this mass range should instead undergo pair instability supernovae, completely disrupting without leaving remnants. The detection of an 85 solar mass black hole suggests it formed through the merger of smaller black holes rather than direct stellar collapse. This implies a hierarchical formation process where black holes grow through successive mergers, building up mass in steps. The final 142 solar mass black hole from GW 190521 represents a confirmed intermediate mass object, but it likely did not remain isolated for long. Depending on its environment, it could merge with additional black holes, climbing further up the mass ladder, or it could drift in relative isolation, accreting gas slowly while awaiting another merger opportunity. The merger rate in typical environments for such objects remain unknown, limiting our understanding of how common intermediate mass black holes are throughout the universe. Globular clusters represent prime hunting grounds for intermediate mass black holes because their dense cores provide both formation pathways and potential detection methods. Astronomers search for intermediate mass black holes in globular clusters by measuring the velocities of stars near cluster centers. If an intermediate mass black hole sits at the core, its gravity will accelerate nearby stars to higher velocities than would occur without the black hole's mass. By carefully measuring stellar velocities using spectroscopy, astronomers can infer the presence of massive dark objects. The globular cluster 47 Tucanae has been extensively studied for signs of a central intermediate mass black hole, located approximately 13,000 light-years from Earth. This cluster contains several million stars packed into a region about 120 light-years across. Early studies suggested the cluster might harbor an intermediate mass black hole with a mass of several thousand solar masses, based on stellar velocity measurements and the cluster's overall mass distribution. However, more recent observations using the Hubble Space Telescope found no convincing evidence for such a massive central object. The stellar motions can be explained by the gravitational effects of the distributed stellar population without requiring a central black hole. Other globular clusters show more promising signatures. The cluster Omega Centauri, the most massive globular cluster in the Milky Way, with approximately 10 million solar masses, exhibits stellar velocity patterns consistent with a central intermediate mass black hole containing approximately 40,000 solar masses. Multiple independent studies using different techniques have found similar mass estimates, strengthening the case that Omega Centauri harbors an intermediate mass black hole. If confirmed, this would make Omega Centauri a powerful laboratory for studying intermediate mass black holes in detail. The globular cluster G1 contains particularly strong evidence for an intermediate mass black hole. Observations show a concentration of stellar mass black holes at the cluster center, suggesting that massive objects have sunk to the core through dynamical friction. The velocity dispersion of these stellar mass black holes implies the presence of an even more massive object with a mass of approximately 4,000 solar masses. This central object is too massive to be a stellar mass black hole and too compact to be explained by the sum of individual stellar mass black holes without invoking a merged intermediate mass progenitor. The demographics of intermediate mass black holes remain poorly constrained. If they form primarily in globular clusters through runaway collisions, their abundance should correlate with globular cluster populations. The Milky Way contains approximately 150 globular clusters, suggesting there could be dozens of intermediate mass black holes associated with these systems. Extrapolating to the broader universe, with hundreds of billions of galaxies each hosting hundreds of globular clusters, the total population of intermediate mass black holes could number in the trillions. But not all intermediate mass black holes need to reside in globular clusters. Some may drift freely through galactic halos, ejected from their birth sites through gravitational recoil during mergers. Others may have formed in the early universe through direct collapse and subsequently been incorporated into forming galaxies. Still others might lurk in dwarf galaxies, the smallest galaxies in the universe, where they could represent the central massive objects analogous to supermassive black holes in larger galaxies. The dwarf galaxy Leo 1, located approximately 800,000 light-years from Earth, shows evidence for a central black hole with a mass of approximately 3 million solar masses. This mass is intermediate between typical stellar mass black holes and the supermassive black holes in giant galaxies, though it sits at the high end of the intermediate mass range. The presence of such a massive black hole in a dwarf galaxy raises questions about black hole-galaxy coevolution and whether the relationships observed in large galaxies extend to the smallest stellar systems. Intermediate mass black holes may serve as the seeds for supermassive black holes. If intermediate mass black holes formed in large numbers in the early universe, they could have provided starting points for the growth of the supermassive black holes we observe in distant quasars. An intermediate mass black hole with a mass of 10,000 solar masses accreting at the Eddington limit could grow to 1 billion solar masses in approximately 1 billion years, potentially explaining how the earliest quasars became so massive so quickly. This seed scenario requires that intermediate mass black holes were common in the early universe and that they efficiently settled into the centers of forming galaxies where they could access abundant gas for accretion. Cosmological simulations suggest this process is plausible, but depends sensitively on the initial conditions and the efficiency of black hole mergers during galaxy formation. If most galaxies in the early universe contained intermediate mass black hole seeds, it would explain the ubiquity of supermassive black holes in modern galaxy centers. The gravitational wave signatures of intermediate mass black hole mergers differ from those of stellar mass mergers. The larger masses produce lower frequency gravitational waves with peak frequencies in the range of tens of hertz rather than hundreds of hertz. These lower frequencies are still within the sensitive band of LIGO and Virgo, but future space-based detectors like LISA, the Laser Interferometer Space Antenna, will be optimized for detecting mergers in this mass range. LISA's launch, planned for the 2030s, will open a new window on intermediate mass black hole populations and their merger rates. The environments where intermediate mass black holes merge affect the gravitational wave signals. Mergers in dense stellar environments can occur in the presence of matter, creating electromagnetic counterparts that would be absent from mergers in empty space. Gas surrounding the merging black holes can emit light as it gets shock heated by the merger, creating potential optical, X-ray, or radio signals that arrive in coincidence with the gravitational waves. The detection of such multi-messenger signals would provide rich information about the merger environment and the properties of the black holes involved. Intermediate mass black holes could also interact with compact objects other than black holes. An intermediate mass black hole could capture a neutron star and slowly consume it through repeated close passages, creating a unique gravitational wave signal. Or it could disrupt a white dwarf through tidal forces, creating a distinctive X-ray or optical transient. These exotic interactions remain largely unexplored observationally, but represent potential discovery channels for intermediate mass black holes in the coming decades. The spin of intermediate mass black holes depends on their formation history. If they formed through direct collapse, their spin would be determined by the angular momentum of the collapsing gas cloud, likely producing moderate spin rates. If they formed through runaway stellar collisions, their spin would reflect the chaotic mergers of multiple objects with random orientations, potentially producing low spin rates. If they grew through hierarchical black hole mergers, their spin could range from low to near maximal depending on the merger history. Measuring spin requires detecting specific signatures in X-ray spectra or gravitational wave signals, techniques that are just becoming feasible for intermediate mass black holes. The accretion disks around intermediate mass black holes occupy a regime intermediate between stellar mass and supermassive black holes. The inner edge of the disk, where gas orbits at nearly the speed of light, has a temperature determined by the black hole's mass. For intermediate mass black holes, this temperature falls in the ultraviolet part of the spectrum, making them potentially bright in ultraviolet light if they have access to fuel. But most intermediate mass black holes likely exist in low-density environments with little available gas, keeping them dark and difficult to detect, except through their gravitational influence. The future of intermediate mass black hole astronomy is promising. Improved gravitational wave detectors will find more mergers involving these objects, constraining their population and formation channels. Next-generation X-ray telescopes will detect fainter ultraluminous X-ray sources and measure their properties more precisely. Radio telescopes will search for jets launched by intermediate-mass black holes in dense stellar environments, and direct imaging of stellar motions in globular clusters using extremely large ground-based telescopes and space-based observatories will reveal the hidden mass at cluster centers. The gap in the mass spectrum may be filling in, with intermediate-mass black holes transitioning from hypothetical objects to confirmed members of the black hole zoo. Their existence proves that nature can create gravitational monsters through pathways beyond simple stellar collapse, and their role as potential seeds for supermassive black holes makes them crucial to understanding the assembly of the largest structures in the universe. But the mass spectrum of black holes extends in both directions from these intermediate objects, reaching scales that dwarf supermassive black holes and shrinking to sizes smaller than atoms. Before the first star ignited, before galaxies assembled from the cosmic web, before matter even formed atoms, the universe may have been seeded with black holes. These objects did not form from collapsing stars or merging gas clouds. They crystallized directly from the quantum foam in the first trillionth of a second after the Big Bang, emerging from density fluctuations so extreme that regions of space-time collapsed into singularities while the cosmos was still smaller than a grapefruit. These are primordial black holes, and they represent the most ancient objects that could possibly exist in the universe. Primordial black holes occupy a unique position in the taxonomy of gravitational monsters because they are not constrained by the normal mass limits that govern stellar or supermassive black holes. A primordial black hole could have any mass from a few micrograms to thousands of solar masses, depending on when it formed after the Big Bang. The smallest would be far tinier than atoms, containing less mass than a grain of sand. The largest could rival supermassive black holes. And unlike every other type of black hole, primordial black holes remain entirely hypothetical. No confirmed detection exists. Yet the theoretical case for their existence grows stronger with each passing year. The formation mechanism for primordial black holes is radically different from anything else in astrophysics. In the first microsecond after the Big Bang, the universe was a roiling plasma of fundamental particles at temperatures exceeding 10 trillion degrees Kelvin. Quantum fluctuations in this primordial soup created regions of slightly higher and lower density. Most of these fluctuations smoothed out as the universe expanded. But in rare locations where the density reached a critical threshold, gravity overwhelmed the radiation pressure, and the overdense region collapsed directly into a black hole. The mass of a primordial black hole depends on the horizon mass at the time of formation. The horizon mass is the total amount of matter contained within the particle horizon, the maximum distance light could have traveled since the Big Bang. This distance increases with time, so the horizon mass grows as the universe ages. A primordial black hole forming at 1 microsecond after the Big Bang would have a mass of approximately 1,000 kilograms, roughly the mass of a large asteroid compressed into a region smaller than a proton. A primordial black hole forming at 1 second after the Big Bang could contain a solar mass. Objects forming later could be even more massive. The distribution of primordial black hole masses depends on the spectrum of density fluctuations in the early universe. Standard inflation models predict that density fluctuations should be small and smoothly distributed across scales, making primordial black hole formation extremely rare. But alternative inflation scenarios allow for enhanced fluctuations at specific scales, potentially producing large populations of primordial black holes with characteristic masses. If such enhanced fluctuations occurred, primordial black holes could represent a significant fraction of the universe's total mass. The most tantalizing possibility is that primordial black holes constitute some or all of the dark matter. Dark matter makes up approximately 85% of all matter in the universe, yet its nature remains unknown. It does not emit, absorb, or reflect light. It interacts only through gravity. Primordial black holes fit these requirements perfectly. A universe filled with primordial black holes ranging from asteroid mass to solar mass could explain all the gravitational effects attributed to dark matter without requiring exotic particles. This hypothesis gained attention in 2016 when LIGO detected the merger of two 30 solar mass black holes, GW150914. The detection revealed that stellar mass black holes in this mass range exist in nature and can merge within the age of the universe. Some theorists propose that these black holes could be primordial in origin rather than formed from stellar collapse. If primordial black holes with masses of tens of solar masses are common, they could account for dark matter while also explaining LIGO's detection rate. But the dark matter hypothesis faces severe constraints from multiple observations. If primordial black holes in the stellar mass range made up all dark matter, they would cause frequent gravitational microlensing events as they pass between Earth and distant stars. Surveys searching for such events have found far fewer lensing detections than expected. For a large primordial black hole population, these null results rule out primordial black holes as the dominant dark matter component for masses above approximately 1 solar mass. Smaller primordial black holes, with masses between 10 to the power of 17 and 10 to the power of 23 kilograms, remain viable dark matter candidates. Objects in this mass range are too small to produce detectable microlensing, but too massive to have evaporated through Hawking radiation. They would cluster in galactic halos like other forms of dark matter, contributing to galaxy rotation curves and gravitational lensing without producing observable electromagnetic signatures. Recent studies suggest that primordial black holes in this mass window could constitute up to 10% of dark matter without violating observational constraints. The smallest primordial black holes face a different fate than their larger cousins. Stephen Hawking demonstrated in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon, with a temperature inversely proportional to mass. For stellar mass black holes, this Hawking temperature is negligibly small, but for microscopic primordial black holes, the temperature becomes significant. A primordial black hole with a mass of 10 to the power of 15 kilograms, roughly the mass of a large mountain, has a Hawking temperature of approximately 120 degrees Kelvin, cold by everyday standards, but hot enough to emit noticeable radiation. As a black hole radiates through Hawking emission, it loses mass, which increases its temperature, which accelerates radiation in a runaway process. The evaporation time is proportional to the cube of the initial mass. Primordial black holes with initial masses below approximately 10 to the power of 15 kilograms would have evaporated completely by now, 13.8 billion years after the Big Bang. At the moment of final evaporation, the black hole releases all its remaining mass energy in a burst of high-energy particles and gamma rays. These evaporation explosions create a potential detection signature. If primordial black holes formed with a range of masses including objects near the evaporation threshold, some should be exploding in the present epoch. Gamma-ray telescopes, like the Fermi Gamma-ray Space Telescope and ground-based Air-Cherenkov telescopes, search for these primordial black hole explosions by looking for characteristic gamma-ray bursts with specific energy spectra. No confirmed detections exist, placing upper limits on the abundance of evaporating primordial black holes. The lack of evaporation signatures rules out certain primordial black hole formation scenarios. If inflation produced copious numbers of microscopic black holes in the evaporating mass range, we should see frequent explosions distributed randomly across the sky. The absence of such signals constrains the spectrum of primordial density fluctuations and limits how many small primordial black holes could have formed. But it does not rule out larger primordial black holes that evaporate too slowly to have disappeared yet. Primordial black holes could have played a crucial role in cosmic structure formation. If they formed in large numbers, they would have acted as gravitational seeds around which normal matter could collapse. The earliest stars might have formed in halos of primordial black holes rather than dark matter particles. Primordial black holes could have merged with each other or accreted gas, growing into the intermediate mass and supermassive black holes observed today. This scenario elegantly explains how supermassive black holes reached billions of solar masses by the time the universe was less than 1 billion years old. Computer simulations of structure formation, including primordial black holes, show that these objects can significantly affect the growth of cosmic structure. Primordial black holes cluster gravitationally like dark matter particles, but can also merge through gravitational wave emission, creating a population that evolves over cosmic time. In simulations with substantial primordial black hole populations, galaxy formation accelerates because gas can cool and collapse into the deep potential wells created by primordial black hole clusters. This could explain why some early galaxies appear surprisingly massive and mature. The formation environments for primordial black holes are exotic by any standard. In the first microsecond after the Big Bang, the universe was in a phase called the radiation-dominated era, where energy density was dominated by photons and relativistic particles rather than matter. The physics governing this epoch is well tested through particle accelerators and cosmological observations, but the extreme densities and temperatures push into regimes where new physics might emerge. One mechanism for generating the necessary density fluctuations invokes phase transitions in the early universe. As the cosmos cooled through specific temperature thresholds, the vacuum state of quantum fields could have changed abruptly, like water freezing into ice. These phase transitions can create bubble walls that collide and merge, generating density perturbations large enough to collapse into black holes. Depending on the details of the phase transition, the resulting primordial black holes could have a narrow mass distribution, all forming with similar masses determined by the horizon size at the transition temperature. Another mechanism involves the production of cosmic strings, one-dimensional topological defects predicted by some grand unified theories. Cosmic strings are linear concentrations of energy density that can stretch across cosmic distances. When cosmic string loops form and collapse, they can create regions of extreme density capable of forming primordial black holes. This mechanism naturally produces black holes with a wide range of masses depending on the loop size, potentially explaining why primordial black holes might span orders of magnitude in mass. Inflation itself can generate primordial black holes if the inflaton field, the hypothetical field driving cosmic inflation, experiences specific fluctuations. Near the end of inflation, quantum fluctuations in the inflaton field can create localized regions where inflation ends slightly earlier or later than the surroundings. These variations translate into density perturbations after inflation ends. If the perturbations are large enough, they collapse into primordial black holes. This inflationary primordial black hole production is highly model-dependent, occurring only for specific choices of inflaton potential. The observational evidence for primordial black holes remains indirect and controversial. Several anomalies in astrophysical observations have been tentatively attributed to primordial black holes, but alternative explanations exist for each. The LIGO-Virgo detections of black hole mergers could include primordial black holes, but distinguishing primordial from stellar origin black holes using gravitational wave signals alone is challenging. The two populations would have different spatial distributions and formation rates, but current detectors lack the sensitivity to measure these differences conclusively. Ultra-faint dwarf galaxies, the smallest galaxies in the universe, show dark matter distributions that some researchers argue are more consistent with primordial black holes than with standard cold dark matter particles. These galaxies contain only a few thousand to a few 100,000 stars, but appear to have dark matter masses hundreds of times larger. If their dark matter halos consist primarily of primordial black holes, the discrete nature of the black hole population would create different gravitational dynamics than a smooth dark matter distribution. However, simulations using standard dark matter also reproduce many properties of ultra-faint dwarfs, and distinguishing between scenarios requires more precise measurements. The abundance of supermassive black holes in the early universe has been cited as indirect evidence for primordial black hole seeds. Quasars observed when the universe was less than 1 billion years old host black holes with masses exceeding 1 billion solar masses. Growing such massive black holes from stellar remnants through accretion appears difficult within the available time. But if these quasars host primordial black holes that formed with initial masses of thousands or millions of solar masses, the growth timescale problem is significantly eased. The primordial seeds could grow to observed masses through normal accretion processes occurring over hundreds of millions of years. Gravitational wave astronomy offers the most promising avenue for detecting primordial black holes and distinguishing them from stellar origin black holes. The merger rate of primordial black hole binaries depends on their spatial distribution and initial clustering, which differ from stellar mass black holes. As LIGO and Virgo accumulate more detections, statistical analysis of the mass distribution, spin distribution, and spatial distribution of merging black holes will constrain how many could be primordial in origin. The spin of primordial black holes provides a potential discriminant. Stellar mass black holes form from collapsing stars with significant angular momentum, producing black holes that spin at moderate to high rates. Primordial black holes form from the collapse of nearly spherical overdense regions with minimal angular momentum, likely producing slowly spinning or non-spinning black holes. If LIGO detects a population of merging black holes with systematically low spins, it would favor a primordial origin. Current data are consistent with both spinning and non-spinning populations, and more detections are needed to draw firm conclusions. The eccentricity of black hole binary orbits offers another test. Black holes that form in isolation and pair through dynamical capture in dense environments should have eccentric orbits when they enter the LIGO detection band. Black holes that form as bound binaries through stellar evolution should have circularized orbits. Primordial black hole binaries that formed in the early universe through random clustering would have a distribution of eccentricities depending on their formation history. Measuring orbital eccentricity from gravitational wave signals is challenging, but possible with improved detector sensitivity. Future gravitational wave detectors will dramatically expand the accessible parameter space for primordial black hole searches. The Einstein Telescope and Cosmic Explorer next-generation ground-based detectors planned for the 2030s and 40s will detect mergers across the entire universe with exquisite precision. LISA, the space-based detector launching in the 2030s, will observe mergers of intermediate mass and massive black holes, probing mass ranges where primordial black holes could explain supermassive black hole formation. These instruments will either confirm primordial black holes as a real population or rule them out across most of the viable parameter space. The effects of primordial black holes on their environments depend strongly on their mass and abundance. Solar mass primordial black holes drifting through the galaxy could occasionally pass close to stars, disrupting planetary systems through gravitational perturbations. A primordial black hole passing within a few astronomical units of the solar system would alter planetary orbits measurably. Searches for anomalies in the orbital dynamics of outer solar system objects have been used to constrain the abundance of nearby primordial black holes, with null results placing limits on how many could exist in the solar neighborhood. Smaller primordial black holes with masses comparable to asteroids could be captured by stars or planets. A primordial black hole captured by Earth would sink to the planet's core through dynamical friction, taking approximately 1 billion years to reach the center. Once at the core, it would begin accreting matter, eventually consuming the entire planet from the inside out. The timescale for complete consumption depends on the black hole's mass and the accretion rate, but for typical parameters, Earth would survive for billions to trillions of years before being destroyed. The lack of evidence for planets being consumed by internal black holes places constraints on the abundance of very small primordial black holes. The possibility that primordial black holes constitute dark matter has profound implications for fundamental physics. If dark matter is primordial black holes rather than exotic particles, it would eliminate the need for physics beyond the standard model to explain dark matter. No supersymmetry, no axions, no weakly interacting massive particles. The dark matter problem would reduce to a cosmological problem about the initial conditions of the universe rather than a particle physics problem requiring new fundamental forces or fields. But this resolution comes at a cost. Explaining why the universe produced the right abundance of primordial black holes to match observed dark matter density requires fine-tuning the spectrum of primordial density fluctuations. Standard inflation models do not naturally produce such fluctuations without modification. Alternative models exist that enhance fluctuations at specific scales, but they introduce additional free parameters that must be justified by theoretical considerations or observational evidence. The hunt for primordial black holes continues across multiple fronts. Gravitational wave observatories monitor the sky for mergers. Gamma-ray telescopes search for evaporation bursts. Microlensing surveys track millions of stars for the telltale brightening caused by black holes passing in front. Radio telescopes look for ultra-compact sources that could be accreting primordial black holes. And theorists refine formation models, calculating predictions that can be tested against observations. The verdict on primordial black holes remains open. They could be common throughout the universe, contributing significantly to dark matter and seeding supermassive black hole formation. Or they could be rare oddities, formed in tiny numbers during brief exotic phases in the early universe. Or they might not exist at all, forever remaining mathematical possibilities unsupported by observational reality. But the search for these ancient ghosts continues because their existence or absence teaches us fundamental truths about the first moments of cosmic history and the mechanisms that shaped the universe we inhabit. Primordial black holes represent the ultimate archaeological artifacts, objects encoding information about physical processes occurring when the universe was less than a second old. If they exist, they are older than atoms, older than light, older than time itself in any meaningful human sense. They are witnesses to the moment of creation, frozen remnants of the Big Bang that have persisted across 13.8 billion years of cosmic evolution. And their discovery would represent one of the most profound confirmations of our cosmological theories, proving that we understand the universe's earliest moments with quantitative precision. Every black hole in the universe spins. This is not a theoretical prediction or an observational uncertainty. It is a mathematical certainty imposed by the conservation of angular momentum. When a star collapses or gas clouds merge, they carry rotational energy that cannot be destroyed. That rotation survives the transition into the black hole, warping the geometry of spacetime in ways that make non-rotating black holes look simple by comparison. These are Kerr black holes, named after New Zealand mathematician Roy Kerr, who solved Einstein's equations for rotating black holes in 1963. And they represent the true nature of gravitational monsters in our universe. A non-rotating black hole is a perfect sphere with a single event horizon marking the boundary of no return. The singularity at the center is a point of zero volume and infinite density. The geometry is elegantly simple, described completely by a single parameter, the mass. But rotation destroys this simplicity. A rotating black hole becomes oblate, flattened at the poles and bulging at the equator. The singularity stretches into a ring rather than a point. And a new region appears outside the event horizon where the fabric of spacetime itself is dragged along with the black hole's spin. This region is called the ergosphere, and it creates possibilities that non-rotating black holes cannot achieve. The mathematics describing rotating black holes is significantly more complex than the Schwarzschild solution for non-rotating objects. Karl Schwarzschild solved Einstein's field equations for a spherically symmetric mass in 1916, just months after Einstein published general relativity. And while Schwarzschild was serving on the Eastern Front during World War I, his solution described the spacetime geometry around non-rotating black holes with elegant simplicity. But adding rotation requires solving Einstein's equations without the simplifying assumption of spherical symmetry, a mathematical challenge that resisted solution for nearly 50 years. Roy Kerr achieved the breakthrough in 1963 while working at the University of Texas at Austin. His solution describes the space-time geometry around a rotating mass and remains one of the most important exact solutions of Einstein's field equations. The Kerr metric, as it is called, contains two parameters, the mass and the angular momentum. Together, these determine the black hole's event horizon size, the ergosphere extent, and the singularity structure. The solution revealed that rotating black holes possess fundamentally different properties than their non-rotating counterparts. The spin of a black hole is quantified by a dimensionless parameter ranging from 0 to 1, where 0 represents no rotation and 1 represents the maximum possible rotation rate. This maximum spin limit exists because faster rotation would cause the event horizon to disappear, exposing the singularity to the outside universe. Roger Penrose proved in 1969 that such naked singularities cannot form from reasonable physical processes, a principle called cosmic censorship. Nature, it seems, forbids us from directly observing singularities, always clothing them behind event horizons. A maximally rotating black hole spins so fast that its equator moves at the speed of light. At this extreme rotation rate, the event horizon shrinks to its minimum possible size for a given mass, and the ergosphere extends furthest into space. The singularity becomes a ring lying in the equatorial plane, a structure topologically distinct from the point singularity of non-rotating black holes. Matter falling into a maximally rotating black hole could theoretically pass through the ring's singularity rather than colliding with a point, entering regions of space-time with bizarre properties, predicted by general relativity but difficult to interpret physically. The ergosphere represents the most distinctive feature of rotating black holes. This region exists outside the event horizon where space-time is dragged so strongly by the black hole's rotation that nothing can remain stationary relative to distant observers. Even light emitted in the ergosphere gets pulled along in the direction of rotation. An observer in the ergosphere would find that staying in place requires moving faster than light, which is impossible. Everything in the ergosphere must orbit the black hole in the direction of spin, though escape remains possible for objects with sufficient velocity pointing outward. The boundary of the ergosphere is called the static limit, the surface where space-time dragging becomes so extreme that static observers can no longer exist. Between the static limit and the event horizon lies the ergosphere, a shell-shaped region thickest at the equator and vanishing at the poles. The size of the ergosphere depends on the black hole's spin rate. For slowly rotating black holes, the ergosphere is small and hugs the event horizon closely. For rapidly rotating black holes, it extends significantly farther into space. Penrose realized in 1969 that the ergosphere allows for energy extraction from rotating black holes through a process now called the Penrose process. An object entering the ergosphere can split into two pieces, with one piece falling into the black hole while the other escapes. If the trajectory is arranged correctly, the escaping piece can carry away more energy than the original object possessed, with the extra energy extracted from the black hole's rotational energy. This process slows the black hole's spin while converting rotational energy into kinetic energy of the escaping fragment. The Penrose process is not merely theoretical speculation. It provides the mechanism for some of the most energetic phenomena in the universe, relativistic jets launched by rotating black holes. When a rotating black hole is surrounded by an accretion disk threaded with magnetic fields, the combination of rotation and magnetism creates a natural particle accelerator. The black hole's spin twists the magnetic field lines into tight spirals that act like electromagnetic rails, flinging particles outward at velocities approaching the speed of light. This process was described in detail by Roger Blandford and Roman Znajek in 1977. The Blandford-Znajek mechanism shows that rotating black holes can convert up to 29% of their rest mass energy into jet power through electromagnetic processes occurring in the ergosphere. This efficiency far exceeds nuclear fusion, which converts less than 1% of mass to energy. A supermassive black hole with a mass of 1 billion solar masses spinning at maximum rate could theoretically extract approximately 300 million solar masses worth of energy as it spins down to zero rotation. Observational evidence for rapidly rotating black holes comes primarily from X-ray observations of accretion disks. The inner edge of an accretion disk around a black hole depends on the black hole's spin. For non-rotating black holes, the innermost stable circular orbit lies at 3 times the Schwarzschild radius, the radius of the event horizon for non-rotating black holes. Gas cannot orbit stably closer than this limit, and instead plunges directly into the black hole. But for rotating black holes, the innermost stable circular orbit moves closer to the event horizon, approaching it asymptotically as spin increases toward maximum. The location of the inner disk edge affects the X-ray spectrum emitted by the hot gas. As gas orbits closer to the event horizon, gravitational redshift and Doppler effects distort the emission lines in characteristic ways. By measuring these distortions using X-ray spectroscopy, astronomers can infer the location of the inner disk edge and thereby determine the black hole's spin. This technique, called X-ray reflection spectroscopy, has been applied to dozens of black holes in binary systems and active galactic nuclei. The stellar mass black hole in the system Cygnus X1 rotates at approximately 85% of the maximum possible rate. The supermassive black hole at the center of the galaxy NGC 1277 spins even faster, at approximately 98% of maximum. These rapid rotation rates are common, suggesting that most black holes in the universe are Kerr black holes rather than Schwarzschild black holes. The rotation results from the angular momentum of the material that formed the black hole and from subsequent accretion of rotating matter. Black hole spin can also be measured through gravitational wave observations. When 2 black holes merge, the gravitational wave signal encodes information about both masses and both spins. The merger produces a final black hole whose mass and spin are determined by conservation of energy and angular momentum. By measuring the gravitational wave frequency and amplitude evolution, scientists extract the component spins and verify that the final black hole spin matches predictions from general relativity. The first gravitational wave detection, GW150914, revealed that the merging black holes had dimensionless spin parameters of approximately 0.3 to 0.4, indicating moderate rotation rates. The final black hole produced by the merger had a spin of approximately 0.7, significantly higher than the progenitors. This spin-up occurs because the orbital angular momentum of the binary system gets absorbed by the merged black hole, increasing its rotation. Nearly all black hole mergers detected by LIGO and Virgo have shown evidence of spin, confirming that rotation is a universal property of black holes. The spin evolution of black holes depends on their accretion history. A black hole accreting gas from a thin accretion disk with consistent orientation will gradually spin up as the accreted material carries angular momentum into the black hole. Over time, this process can drive the spin toward maximum. But if the accretion occurs from random directions, with the disk orientation changing over time, the black hole's spin axis will wobble, and the spin magnitude may not increase efficiently. Chaotic accretion can even spin down a black hole if material falls in with angular momentum opposite to the black hole's spin. Black hole mergers also affect spin in complex ways. When 2 black holes with aligned spins merge, the final black hole typically spins faster than either progenitor. But if the spins are misaligned or anti-aligned, the merger can produce a slowly rotating final black hole. The gravitational wave signal encodes this spin information through subtle modulations in the waveform that depend on how the black hole's spins interact with the orbital motion. The spin of supermassive black holes likely reflects their merger and accretion histories over billions of years. Supermassive black holes that grew primarily through steady accretion from geometrically thin disks should be rapidly rotating, approaching maximum spin. Those that grew through chaotic accretion or multiple major mergers with random orientations may have lower spins. Measuring the spins of supermassive black holes across cosmic time provides information about how these objects assembled and how gas fed into galactic nuclei. The Event Horizon Telescope imaging of the supermassive black holes in M87 and Sagittarius A* provides constraints on their spins. Through the appearance of the photon rings surrounding the event horizon, the ring's shape and brightness distribution depend on the black hole's spin and the viewing angle. Initial analysis of the M87 image suggests moderate to high spin, consistent with X-ray measurements, though degeneracies between spin and viewing angle complicate precise determination. The frame-dragging effect near rotating black holes has been measured experimentally near Earth using the Gravity Probe B satellite launched in 2004. The satellite carried ultra-precise gyroscopes that measured how Earth's rotation drags space-time, causing the gyroscope orientations to drift over time. The measured drift matched general relativity's predictions to within 1%, confirming frame dragging in the weak field regime. Near black holes, frame dragging becomes extreme, dominating the space-time geometry in the ergosphere. An astronaut falling into a rotating black hole would experience frame dragging as a force pulling them sideways, forcing them to orbit in the direction of the black hole's spin. Fighting this rotation would be futile. The space-time itself is rotating, and moving against it would require velocities exceeding light speed. The astronaut would spiral around the black hole as they fell inward, their orbital velocity increasing until they crossed the event horizon. Inside the horizon, the singularity would lie ahead in time rather than in space, and reaching it would become as inevitable as reaching the next moment. The interior structure of rotating black holes differs radically from non-rotating ones. Mathematical extensions of the Kerr solution suggest that the ring singularity encloses regions of space-time with closed time-like curves, packs that loop back on themselves in time. An observer passing through the ring singularity could theoretically travel backward in time, creating causality paradoxes. Whether such time travel is physically realizable remains unknown, as quantum effects near the singularity likely prevent classical general relativity from accurately describing the geometry. Some solutions to Einstein's equations for rotating black holes contain inner horizons in addition to the outer event horizon. The region between these horizons has unusual properties, including areas where the direction of time changes. These inner horizon solutions are mathematically valid but physically questionable. Small perturbations likely destabilize inner horizons, causing them to collapse or preventing their formation. The realistic interior structure of rotating black holes remains an open question, requiring a theory of quantum gravity to fully resolve. The maximum spin limit for black holes can be approached but not exceeded by astrophysical processes. Accretion of matter naturally spins up black holes, but as the spin increases, the innermost stable circular orbit moves closer to the event horizon. Eventually, the disk becomes so compact that radiation pressure and magnetic stresses limit further accretion, preventing the black hole from spinning beyond the maximum. Similarly, black hole mergers can produce rapidly spinning remnants, but the final spin cannot exceed the maximum value consistent with the event horizon existing. Theoretical proposals exist for spinning down black holes through counter-rotating accretion or through the Penrose process, but these mechanisms are inefficient in most astrophysical contexts. A black hole embedded in a strong magnetic field threading an accretion disk will naturally launch jets that extract rotational energy, slowly reducing the spin over millions of years. But typical accretion rates and magnetic field strengths suggest spin-down timescales comparable to the black hole's growth timescale, meaning black holes remain rapidly rotating throughout most of their lives. The population of black hole spins across the universe provides a fossil record of formation channels and evolution pathways. Stellar mass black holes formed from single star collapse should have spins determined by the progenitor star's rotation and angular momentum transport during collapse. Black holes formed from binary stellar evolution may have different spin distributions depending on mass transfer history and tidal interactions before collapse. Black holes formed from mergers of earlier generations should exhibit spins reflecting the merger dynamics. Distinguishing these formation channels through spin measurements remains challenging because multiple pathways can produce similar spin distributions. But as the gravitational wave catalog grows to hundreds and thousands of detections, statistical analysis of spin populations will constrain formation mechanisms. Already, the observed spins from LIGO-Virgo detections suggest that some black holes may have formed through hierarchical mergers rather than direct stellar collapse, though definitive conclusions require larger samples. Rotating black holes represent the true form of gravitational singularities in nature. Non-rotating black holes are mathematical idealizations, unstable to any perturbation that adds angular momentum. Every black hole in the universe spins, warping space-time around it in ways that enable energy extraction, generate powerful jets, and create regions where space itself cannot stand still. Understanding rotating black holes is essential to understanding black hole physics because Kerr black holes, not Schwarzschild black holes, dominate the cosmic census of gravitational monsters. Two black holes are falling toward each other right now, somewhere in the universe, locked in an orbital embrace that will end in catastrophe. They have been circling each other for millions of years, gradually spiraling inward as they radiate gravitational waves. With each orbit, they lose energy, moving closer together, orbiting faster. The process accelerates exponentially. What began as a lazy dance lasting millennia becomes a frenzied spiral lasting seconds. In the final fraction of a second before merger, the two event horizons reach velocities exceeding half the speed of light, warping spacetime so violently that ripples propagate across billions of light years, carrying the news of their death to every corner of the cosmos. Binary black holes represent a class of gravitational systems where two black holes orbit each other, bound by mutual gravitational attraction. These systems form through several pathways, each revealing different aspects of stellar evolution and galactic dynamics. The most common formation channel involves binary star systems, where both stars are massive enough to end as black holes. The two stars evolve together, exchanging mass and angular momentum through their lifetimes. When the first star explodes as a supernova and collapses into a black hole, the second star may remain bound in orbit. Eventually, the second star also explodes and collapses, creating a binary black hole system. The orbital evolution of binary black holes is governed by general relativity, and the predictions are precise and unforgiving. As the black holes orbit, they accelerate massive concentrations of matter through curved spacetime, creating distortions in spacetime geometry that propagate outward as gravitational waves. These waves carry energy and angular momentum away from the binary system, causing the orbit to shrink. The rate of energy loss through gravitational radiation increases dramatically as the black holes move closer together, creating a runaway and spiral that culminates in merger. The timescale for merger depends on the initial orbital separation and the black hole masses. A binary system with two 10 solar mass black holes in a wide orbit separated by 1 astronomical unit would take approximately 10 billion years to merge through gravitational wave emission alone. But if the initial separation is smaller, perhaps due to evolution in a tight stellar binary, the merger timescale decreases dramatically. A separation of 1/10 astronomical unit reduces the merger time to approximately 100 million years. At 100th astronomical unit, merger occurs in just 1 million years. The gravitational wave signal from a binary black hole merger encodes extraordinary amounts of information about the system. The wave frequency corresponds to the orbital frequency, starting low when the black holes are widely separated and increasing as they spiral together. The amplitude of the waves depends on the black hole masses and the distance to the system. By measuring how frequency and amplitude evolve over time, gravitational wave detectors can extract the individual masses, the orbital parameters, the spins of both black holes, and the distance to the merger. The first detection of gravitational waves came on September 14, 2015, when LIGO's two detectors, located in Louisiana and Washington state, simultaneously recorded a signal lasting approximately 0.2 seconds. The signal, designated GW150914, showed the characteristic frequency evolution of an unspiraling binary, starting at 35 Hz and sweeping up to 250 Hz before abruptly cutting off. Analysis revealed that two black holes with masses of approximately 36 and 29 solar masses had merged at a distance of 1.3 billion light-years, creating a final black hole of 62 solar masses. The missing 3 solar masses did not disappear. They converted entirely to gravitational wave energy, according to Einstein's mass-energy equivalence. During the final tenth of a second of the merger, the system radiated gravitational wave power exceeding the combined luminosity of all stars in the observable universe. For that brief moment, the merger outshone the entire electromagnetic universe by a factor of 50, though the power emerged as space-time vibrations rather than light. The peak gravitational wave luminosity reached approximately 3.6 times 10 to the power of 49 watts, a number almost incomprehensible in human terms. The detection confirmed a century of theoretical predictions and opened an entirely new window on the universe. For the first time, humanity observed the universe through gravitational waves rather than light, accessing phenomena that emit no electromagnetic radiation. Black hole mergers are invisible to conventional telescopes because black holes themselves emit no light, and the mergers typically occur in empty space, far from any matter that could radiate. Only through gravitational wave astronomy could these events be detected and studied. Since that first detection, LIGO and its partners have observed more than 90 confident gravitational wave signals, the vast majority from binary black hole mergers. Each detection provides a data point for understanding the population of black holes in the universe, their mass distribution, spin distribution, and merger rates. The accumulated observations reveal that binary black holes are common, that their masses span from a few solar masses to over 100 solar masses, and that merger rates are high enough to make detections routine with current instrument sensitivity. The formation of binary black holes through stellar evolution requires specific conditions. The two progenitor stars must be sufficiently massive to produce black holes rather than neutron stars or white dwarfs. They must remain bound throughout their evolution despite receiving kicks from asymmetric supernova explosions that can impart velocities of hundreds of kilometers per second. And they must end up in an orbit tight enough that gravitational wave emission will cause them to merge within the age of the universe. Detailed stellar evolution models show that binary black hole formation is most efficient in low metallicity environments. Heavy elements in stars create strong stellar winds that blow away mass, reducing the final remnant mass. In metal-poor stars, mass loss is less efficient, allowing more massive black holes to form. Metal-poor stars also tend to have smaller radii, making it easier for binary systems to survive the supernova explosions without being disrupted. Observations suggest that many of the black holes detected by LIGO formed in low metallicity stellar populations, consistent with these models. An alternative formation channel involves dynamical assembly in dense stellar environments. In globular clusters and galactic nuclei, stellar mass black holes can sink to the core through dynamical friction and form binaries through three-body interactions. When a single black hole encounters a binary system of two black holes, gravitational interactions can eject one black hole while leaving the other two bound in a tighter orbit. Through repeated encounters, the binary's orbital separation decreases until gravitational wave emission takes over and drives the system to merger. The dynamical formation channel produces binary black holes with different properties than the isolated binary evolution channel. Dynamically formed binaries can have random spin orientations because the black holes came from independent formation events and had no prior relationship. Binaries from stellar evolution typically have more aligned spins because the progenitor stars influenced each other's rotation through tidal interactions and mass transfer. The spin distribution measured by LIGO Virgo shows evidence for both aligned and misaligned systems, suggesting both formation channels contribute to the observed population. The final moments before binary black hole merger are the most violent events in the universe. As the two black holes spiral to within a few hundred kilometers of each other, their orbital velocity reaches appreciable fractions of light speed. The gravitational field becomes so strong that space-time curvature dominates the dynamics. The black holes plunge toward each other, their event horizons deforming from perfect spheres into elongated shapes as tidal forces stretch them. At the moment of contact, the two horizons merge into a single distorted horizon that rings like a struck bell, radiating gravitational waves at frequencies determined by the final black hole's mass and spin. This ring-down phase lasts only milliseconds but encodes information about the final black hole's properties. The ring-down frequencies depend on the black hole's mass and spin according to predictions from general relativity. By measuring these frequencies, scientists verify that the merged object is indeed a black hole, rather than some other compact object. Every detected merger has shown ring-down frequencies consistent with black hole predictions, providing strong evidence that general relativity correctly describes gravity. In the most extreme conditions accessible to observation, the no-hair theorem of black hole physics states that stationary black holes are completely characterized by mass, spin, and charge, with no other distinguishing features. This theorem implies that after merger, all memory of the individual progenitor black holes erases, except for their contributions to the final mass, spin, and charge. The ring-down phase represents the newly merged black hole settling into its final state, radiating away asymmetries and deformations until it becomes a perfect Kerr black hole, described by just two numbers, mass and spin. Binary black hole mergers can produce recoil velocities through asymmetric gravitational wave emission. If the two black holes have different masses or spins oriented in specific configurations, the gravitational waves carry more momentum in one direction than others, giving the merged black hole a kick. Numerical simulations show that maximum recoil velocities can reach 5,000 kilometers per second for optimal mass ratios and spin configurations. Such kicks can eject black holes from globular clusters or even from dwarf galaxies, creating rogue black holes that wander through intergalactic space. The observation of gravitational wave recoil would provide direct evidence of momentum conservation in gravitational interactions. Measuring recoil requires either detecting the merged black hole's motion through Doppler shifts in subsequent signals or observing electromagnetic counterparts that reveal the merger's velocity relative to surrounding matter. No definitive recoil measurements exist yet, but as detector sensitivity improves and the catalog grows, statistical evidence for recoil velocities may emerge from population studies. Hierarchical mergers, where black holes merge repeatedly over cosmic time, represent another fascinating aspect of binary black hole evolution. A black hole formed from merging two smaller black holes can itself merge with another black hole, creating progressively more massive objects. This process could build up intermediate mass and possibly supermassive black holes through successive generations of mergers. Gravitational wave observations provide evidence for hierarchical mergers through the detection of black holes with masses in the pair instability gap, masses that cannot form from single stellar collapse but could arise from earlier mergers. The detection of GW 190521, mentioned in the intermediate mass black hole chapter, exemplifies hierarchical merger evidence. The 85 solar mass progenitor black hole sits squarely in the mass range where pair instability supernovae should prevent black hole formation. The most natural explanation is that this black hole formed from the merger of two smaller black holes, each formed from stellar collapse. The detection of the 85 solar mass object merging with a 66 solar mass partner to create a 142 solar mass remnant demonstrates that hierarchical growth is occurring in the universe. The merger rate of binary black holes has been measured by LIGO Virgo to be approximately 20 to 100 mergers per cubic gigaparsec per year. A gigaparsec is approximately 3.3 billion light-years, so this rate implies that within a volume of space containing roughly 100 billion galaxies like the Milky Way, dozens to hundreds of black hole mergers occur each year. Extrapolating to the entire observable universe, which spans approximately 14 gigaparsecs in radius, suggests millions of black hole mergers occur every year across cosmic distances. The environments where binary black holes merge affect whether electromagnetic counterparts accompany the gravitational wave signal. Most mergers occur in empty space, far from any gas or stars that could produce light. These events are invisible to conventional telescopes and detectable only through gravitational waves. But mergers occurring in dense environments such as the accretion disks of active galactic nuclei could produce electromagnetic signals as the merger disturbs surrounding gas. Searches for optical, X-ray, and radio counterparts to LIGO-Virgo detections have yielded no convincing associations, suggesting that most detected mergers occurred in isolation. The possibility of observing electromagnetic counterparts motivates continued coordinated observations. When LIGO-Virgo detects a candidate gravitational wave signal, alerts go out within minutes to telescopes worldwide, which slew to the sky location and search for transients. So far, black hole mergers have produced no confirmed electromagnetic counterparts, but neutron-star mergers have. The detection of a neutron-star merger, GW170817, was accompanied by a gamma-ray burst and optical transient, demonstrating the power of multi-messenger astronomy. Future black hole mergers in gas-rich environments may eventually produce detectable light. The spins of black holes in binary systems provide clues about formation history and evolution. Measurements from LIGO-Virgo show a wide range of spin magnitudes and orientations. Some systems have large spins aligned with the orbital angular momentum, suggesting they formed from binary stellar evolution. Others have low spins or misaligned spins, consistent with dynamical formation in dense clusters. A few systems show evidence for precession, where the spin axes wobble due to spin-orbit coupling, creating modulations in the gravitational wave signal. The mass distribution of merging black holes extends from approximately 5 solar masses to over 100 solar masses, with a peak around 10 solar masses. This distribution reflects the initial mass function of massive stars modified by selection effects and formation pathways. The upper mass cutoff remains uncertain. Pair instability supernovae should prevent black hole formation above approximately 65 solar masses from single stars, but hierarchical mergers can exceed this limit. The lower mass cutoff connects to the minimum mass for black hole formation, approximately 3 solar masses, below which neutron stars form instead. Binary black holes with extreme mass ratios, where one black hole is much more massive than the other, produce gravitational wave signals with distinct characteristics. The smaller black hole orbits many times before merger, creating a long and spiral signal that encodes precise information about the larger black hole's mass and spin. These extreme mass ratio and spirals are prime targets for future space-based detectors like LISA, which will observe stellar mass black holes spiraling into supermassive black holes over years-long observations. The discovery of binary black holes has revolutionized astrophysics, confirming that black holes exist in nature, that they merge on observable timescales, and that gravitational waves carry information about the most violent events in the universe. The population of binary black holes provides insights into stellar evolution, galactic dynamics, and the assembly of structure across cosmic time. And the continued detection of mergers will map the black hole population with increasing precision, revealing how these objects form, evolve, and shape the universe around them. Binary supermassive black holes form when galaxies merge, bringing together the central black holes from each galaxy. These systems evolve through 3 phases. First, dynamical friction from stars and dark matter in the merged galaxy causes the black holes to spiral toward the center, a process taking millions to hundreds of millions of years. Second, gravitational interactions with individual stars eject stars from the core and extract energy from the binary, shrinking the orbit further. This hardening phase can stall if too few stars remain in the core to remove energy efficiently. Third, if the binary reaches small enough separation, gravitational wave emission dominates and drives rapid merger. The final parsec problem describes the potential stalling of binary supermassive black holes at separations of approximately 1 parsec, roughly 3 light-years. At this separation, the binary has ejected most stars on orbits that could interact efficiently. Without additional mechanisms to remove energy, the binary could persist for timescales exceeding the age of the universe. Proposed solutions include gas accretion, which provides dissipation through dynamical friction with the circumbinary disk, and interactions with a third black hole, which can destabilize the binary and accelerate merger. Gravitational wave observations of supermassive black hole mergers require space-based detectors because the wave frequencies are too low for ground-based instruments. LISA, planned for launch in the 2030s, will detect mergers of black holes from thousands to millions of solar masses across the observable universe. These observations will test general relativity in the strong field regime, constrain supermassive black hole formation scenarios, and provide a census of massive black holes beyond the reach of electromagnetic surveys. Pulsar timing arrays offer another method for detecting low-frequency gravitational waves from supermassive black hole binaries. By precisely measuring the arrival times of radio pulses from multiple pulsars distributed across the sky, astronomers can detect correlated timing variations caused by passing gravitational waves. The North American Nanohertz Observatory for Gravitational Waves, NANOGrav, and similar projects worldwide have reported evidence for a stochastic background of gravitational waves, consistent with a population of merging supermassive black hole binaries. Confirming this signal and detecting individual systems remains an ongoing effort. Binary black holes represent death spirals playing out across the universe on timescales from seconds to billions of years. They are systems where two of the universe's most extreme objects, locked in gravitational embrace, gradually approach oblivion. The merger releases energy exceeding the combined output of every star in the observable universe, all radiated as ripples in space-time geometry. And yet, despite this violence, nothing can escape. No light, no matter, no information. The binary black hole merger is a silent catastrophe, invisible to light but screaming through the geometry of the cosmos itself. There might be a black hole smaller than an atom passing through your body right now. It would contain the mass of a small mountain, compressed into a region 1 billion times smaller than a proton. It would pass through you, through the Earth, through the solar system, without interacting with a single particle of matter, not because it lacks gravity, but because it is so small that the probability of hitting anything is essentially zero. These are microscopic black holes, theoretical objects that exist at the boundary between general relativity and quantum mechanics, where the smooth geometry of space-time begins to break down into quantum foam. Microscopic black holes occupy the mass range below approximately 1 billion kilograms, corresponding to event horizon radii smaller than 1 atometer, 10 to the power of -18 meters. For comparison, a proton has a radius of approximately 1 femtometer, 10 to the power of -15 meters, making microscopic black holes 1,000 times smaller than atomic nuclei. At these scales, quantum effects dominate the physics. Hawking radiation becomes significant, and the distinction between particle and black hole blurs into quantum uncertainty. The formation of microscopic black holes requires conditions far more extreme than anything occurring naturally in the current universe. The density needed to create a microscopic black hole exceeds nuclear density by factors of billions. Such densities may have existed in the first microseconds after the Big Bang, potentially creating primordial black holes in this mass range. But in the current epoch, microscopic black holes could form only through high-energy particle collisions or quantum vacuum fluctuations, processes that remain hypothetical and unobserved. Theoretical proposals in the early 2000s suggested that microscopic black holes might be produced in particle accelerators, if extraspatial dimensions exist beyond the 3 we perceive. In theories with large extra dimensions, gravity becomes much stronger at small scales, lowering the energy threshold for black hole formation. The Large Hadron Collider at CERN, which collides protons at center-of-mass energies of 13 trillion electron volts, was predicted to potentially create microscopic black holes at rates of 1 per second if certain extra-dimension scenarios were correct. The black holes produced in collider experiments would have masses comparable to the collision energy, approximately 10 to the power of minus 23 kilograms, containing roughly the mass equivalent of 10,000 proton masses. The event horizon radius would be approximately 10 to the power of minus 20 meters, far smaller than a proton. These objects would exist for incredibly brief times before evaporating through Hawking radiation. The evaporation time for a 10 to the power of minus 23 kilogram black hole is approximately 10 to the power of minus 96 seconds, a duration so short that even light can travel only 10 to the power of minus 88 meters during the black hole's entire lifetime. The decay products of an evaporating microscopic black hole would include all standard model particles, quarks, leptons, gauge bosons, and possibly Higgs bosons, emitted democratically according to their available phase space. The signature would appear as a spherically symmetric spray of particles with energies comparable to the black hole's temperature, which, for a collider-produced black hole, would be approximately 1 trillion electron volts. Detectors at the Large Hadron Collider searched for such signatures, but found none, ruling out the most optimistic extra-dimension scenarios and placing strong constraints on theories predicting low-scale quantum gravity. The absence of microscopic black hole production at the Large Hadron Collider suggests either that extra dimensions do not exist, that they are smaller than the models predicted, or that the quantum gravity scale is higher than accelerator energies can probe. Current experimental limits indicate that if black holes can form through particle collisions, the threshold energy must exceed 13 trillion electron volts. Future colliders might reach higher energies, but the next generation of machines is unlikely to exceed 100 trillion electron volts, leaving microscopic black hole production firmly in the realm of speculation for the foreseeable future. Hawking radiation becomes the dominant feature of microscopic black holes because their temperatures are high. The temperature is inversely proportional to mass, so as mass decreases, temperature increases. A microscopic black hole with a mass of 1 billion kilograms has a temperature of approximately 120 degrees Kelvin. Cold, but not negligible. A black hole with a mass of 1 million kilograms has a temperature of 120,000 degrees Kelvin, hotter than the surface of most stars. And a black hole with a mass of 1,000 kilograms has a temperature of 120 billion degrees Kelvin, hot enough that its thermal radiation spectrum extends into gamma rays. The evaporation process accelerates as the black hole loses mass. Each photon or particle emitted carries away energy, reducing the black hole's mass, which increases its temperature, which accelerates radiation. In the final moments before complete evaporation, the black hole reaches Planck's scale mass, approximately 10 to the power of minus 8 kilograms, where quantum gravitational effects become dominant. The final burst releases all remaining mass energy in a flash of high-energy particles and radiation. For a black hole that started at 1 billion kilograms, this endpoint occurs approximately 10 to the power of 56 years in the future. For a 1 million kilogram black hole, evaporation completes in approximately 10 to the power of 38 years. The smallest possible black holes are limited by the Planck length and Planck mass, fundamental scales where quantum gravity effects prevent classical black hole descriptions. The Planck mass is approximately 10 to the power of minus 8 kilograms, and the corresponding Planck length is approximately 10 to the power of minus 35 meters. Objects at these scales are neither purely classical black holes nor purely quantum particles, but some hybrid quantum gravitational entity that current physics cannot accurately describe. Understanding Planck-scale black holes requires a complete theory of quantum gravity, which remains elusive despite decades of effort. Virtual black holes are quantum fluctuations of space-time geometry that appear and disappear on timescales shorter than the light-crossing time of their event horizons. Quantum field theory, in curved spacetime, suggests that empty space should be filled with short-lived black hole pairs that pop into existence and annihilate almost immediately, contributing to the quantum foam structure of spacetime at the Planck scale. These virtual black holes do not persist long enough to be observed directly, but they may affect particle physics through quantum corrections to scattering amplitudes and other observables. The information paradox becomes acute for microscopic black holes because they evaporate completely on relatively short timescales. When a black hole forms from matter with specific quantum states and then evaporates completely, the question arises: where did the information about the initial state go? Hawking radiation is thermal, containing no information about what fell into the black hole. If the radiation is truly random, information is destroyed, violating quantum mechanics. If information escapes somehow, it must be encoded in correlations between Hawking radiation particles in ways not yet understood. Proposed resolutions to the information paradox include black hole complementarity, which suggests that information appears destroyed to external observers but survives from the perspective of infalling observers, and firewall proposals, which suggest that the event horizon is replaced by a surface of high-energy excitations that destroy infalling information carriers. Neither resolution is universally accepted, and the paradox remains one of theoretical physics' deepest puzzles. Microscopic black holes could serve as microscopic particle accelerators if they could be created and controlled. Matter falling into a microscopic black hole would be compressed to nuclear densities and beyond, creating conditions unattainable in terrestrial laboratories. The Hawking radiation emitted during evaporation would include particles from energies exceeding current accelerator capabilities. If methods existed to produce and study microscopic black holes, they could probe physics at energy scales otherwise inaccessible until far future colliders reach vastly higher energies. The possibility that microscopic black holes exist as dark matter has been considered but faces severe constraints. If dark matter consisted of microscopic black holes in the mass range where Hawking radiation is significant, their evaporation would produce detectable gamma-ray signals. Searches for these signals have found nothing, ruling out most of the microscopic black hole mass range as a dark matter candidate. Only black holes massive enough to evaporate on timescales longer than the age of the universe remain viable, which requires masses above approximately 10 to the power of 15 kilograms. Pushing into the primordial black hole regime discussed earlier, microscopic black holes might form naturally in the cores of neutron stars if densities exceed thresholds predicted by some theories. A tiny black hole forming at a neutron star's center would gradually accrete the surrounding neutron-rich matter, eventually consuming the entire star and creating a stellar mass black hole. This process would be slow, taking thousands to millions of years depending on the initial microscopic black hole mass and the neutron star density profile. Observational signatures might include sudden changes in neutron star properties or unexpected conversions of neutron stars into black holes without supernova explosions. Quantum black holes are hypothetical objects where quantum gravitational effects dominate completely, preventing classical event horizon formation. In loop quantum gravity and some other quantum gravity approaches, the classical singularity is replaced by a quantum bounce or other regular structure. These quantum black holes might behave quite differently from classical predictions, potentially avoiding information loss paradoxes through quantum mechanical processes that preserve unitarity. Experimental tests of quantum black hole scenarios require either detecting microscopic black holes or observing signatures of quantum gravity in astrophysical black holes, both challenging prospects with current technology. The study of microscopic black holes pushes physics into regimes where general relativity and quantum mechanics must both be considered simultaneously. Classical general relativity breaks down at the Planck scale, and quantum field theory in fixed curved backgrounds becomes inadequate. A complete description requires quantum gravity, the hypothetical theory unifying Einstein's geometric description of gravity with the probabilistic nature of quantum mechanics. String theory, loop quantum gravity, and other approaches attempt this unification, using microscopic black holes as test cases for theoretical predictions. Microscopic black holes represent the ultimate intersection of the very large and the very small. They are objects where gravitational physics meets particle physics, where space-time geometry becomes quantized, where the distinction between matter and void dissolves into quantum uncertainty. They are the smallest predators in the taxonomy of gravitational monsters, existing at scales where the universe itself becomes grainy and discontinuous. Whether they exist in nature remains unknown, but their theoretical properties illuminate the boundaries of our understanding and point toward the quantum structure underlying all of reality. You have journeyed through the taxonomy of cosmic predators, 9 distinct species of gravitational monsters, each one breaking reality in its own unique way. Stellar mass black holes born from collapsing stars, manufacturing 100 million new execution chambers every year across the observable universe. Supermassive black holes anchoring the centers of galaxies, some containing billions of solar masses compressed into regions smaller than our solar system. Intermediate mass black holes bridging the gap between stellar remnants and galactic engines, forming through exotic pathways involving runaway collisions and hierarchical mergers. Primordial black holes that may have formed in the universe's first microsecond, emerging from quantum fluctuations before stars existed, potentially constituting the dark matter that holds galaxies together. Rotating black holes that drag space-time around them like cosmic tornadoes, creating ergospheres where nothing can stand still, and enabling energy extraction through the Penrose process. Charged black holes that probably do not exist in nature, but illuminate the mathematical structure of general relativity through their exotic properties and naked singularities. Binary black holes locked in death spirals, radiating gravitational waves as they spiral toward merger, releasing more power in their final seconds than all stars in the observable universe combined. And microscopic black holes existing at the boundary between quantum mechanics and gravity, where space-time itself becomes quantized, and the smooth geometry of Einstein's equations dissolves into quantum foam. Each type represents a different failure mode of matter and space-time. Each demonstrates that the universe has discovered multiple pathways to create regions where the laws of physics as we understand them cease to function. The event horizon marks not just a boundary in space, but a boundary in reality itself, beyond which causality breaks down, time becomes space, and all futures lead inexorably to the singularity. The total population of black holes in the observable universe exceeds 100 billion objects. Most are stellar mass remnants drifting invisibly through galactic disks and halos. Approximately 100 billion supermassive black holes sit in galaxy centers, with masses ranging from 100,000 to tens of billions of solar masses. Unknown numbers of intermediate mass, primordial, and microscopic black holes may populate the cosmos, each contributing to the gravitational architecture that shapes structure on the largest scales. Together, these objects represent a significant fraction of the universe's total mass budget. The combined mass of all black holes in the observable universe approaches 10 to the power of 16 solar masses, equivalent to millions of galaxies. This mass has been removed from the cosmic census of observable matter, locked behind event horizons where it can never be recovered or observed directly. The universe is gradually converting matter into black holes through stellar evolution, galaxy mergers, and exotic formation channels, accumulating mass in gravitational prisons from which nothing escapes. The future belongs to black holes. In 100 trillion years, after the last stars have exhausted their nuclear fuel and the universe has entered its twilight, black holes will dominate the cosmic mass budget. Stellar remnants will evaporate from galaxies through gravitational interactions, wandering alone through expanding space. Supermassive black holes will sit in the dark cores of dead galaxies, monuments to epochs when stars and light were common. And gradually, incomprehensibly slowly, these objects will evaporate through Hawking radiation. A stellar mass black hole will take 10 to the power of 67 years to evaporate completely. A supermassive black hole containing 1 billion solar masses requires 10 to the power of 96 years. These timescales exceed the current age of the universe by factors so large that comparison becomes meaningless. The black hole era will last longer than the stelliferous era by factors of 10 to the power of 50 or more. For most of the universe's future, black holes will be the only significant structures that exist. The evaporation process will accelerate as black holes shrink. In their final moments, they will reach Planck-scale masses and explode in bursts of high-energy particles, releasing their last whispers of mass energy into an empty, cold universe that has long since forgotten stars and galaxies and life. These final explosions, separated by incomprehensible spans of time, will mark the universe's last moments of significant energy release before heat death imposes eternal equilibrium. But understanding black holes is not merely an academic exercise in mapping the universe's inventory of gravitational monsters. It is an existential confrontation with the limits of knowledge and the boundaries of physical law. Black holes force us to confront questions that challenge the foundations of science. What happens to information that falls into a black hole? Can quantum mechanics and general relativity be unified into a consistent theory of quantum gravity? Do naked singularities exist, or does cosmic censorship prevent us from ever observing them? The event horizon represents an absolute boundary beyond which observation is impossible. An astronaut falling into a black hole cannot send back information about what they observe inside the horizon. From our perspective, they freeze at the event horizon, their image becoming increasingly redshifted until it fades into invisibility. But from their perspective, they cross the horizon in finite time and experience the increasingly strong tidal forces as they approach the singularity. The two perspectives cannot be reconciled using classical physics alone. This complementarity, where different observers have fundamentally different but equally valid descriptions of the same event, hints at deep connections between quantum mechanics, information theory, and gravity. The holographic principle, derived from black hole thermodynamics, suggests that all information in a three-dimensional volume can be encoded on its two-dimensional boundary. This radical idea has led to breakthroughs in string theory and quantum field theory, suggesting that spacetime itself may be emergent from more fundamental quantum information. Black holes also serve as natural laboratories for testing general relativity in the strong field regime. The Event Horizon Telescope images of M87 and Sagittarius A* confirm that supermassive black holes exist, and that their shadows match general relativistic predictions. Gravitational wave detections from LIGO-Virgo test whether merging black holes emit the predicted waveforms and whether the remnants ring down at frequencies determined by mass and spin. Every observation so far confirms Einstein's century-old theory with remarkable precision. Yet general relativity predicts its own breakdown at singularities. The infinite densities and spacetime curvatures of black hole cores cannot be physically real. Quantum gravity must resolve these singularities, replacing the classical prediction with something that remains finite and describable by physical laws. But we do not yet possess a complete theory of quantum gravity, and the interior structure of black holes remains fundamentally unknown. The taxonomy of black holes reveals that the universe is far more creative at destroying information and creating gravitational traps than we ever imagined. The 9 types discussed here may not exhaust all possibilities. Higher dimensional black holes in alternative theories of gravity, and exotic objects that mimic black holes, but lack true event horizons could exist in corners of parameter space we have not yet explored. The search continues for new types of gravitational monsters. Gravitational wave observatories improve their sensitivity, detecting fainter and more distant mergers. X-ray telescopes probe accretion disks around black holes with increasing precision. Radio telescopes map the shadows of supermassive black holes at higher resolution. And theorists develop increasingly sophisticated models of black hole formation, evolution, and evaporation. Each discovery adds another piece to the cosmic puzzle. Each observation tests our theories and pushes the boundaries of what we understand about gravity, quantum mechanics, and the structure of spacetime. And each black hole detected reminds us that the universe operates according to laws that permit the existence of objects so extreme, so alien, that they challenge the very notion of comprehensibility. The black hole is not just an astronomical object. It is a wound in the fabric of reality, a place where the universe has broken itself through its own gravitational force. It is a one-way portal to nowhere, a trapdoor in space-time that swallows everything and releases nothing. It is the ultimate predator, patient and inevitable, waiting at the end of every massive star's life, and at the center of every large galaxy. You are living in a universe that contains 100 billion of these execution chambers. They surround you, invisible and silent, scattered through the darkness between stars. Some are close enough that their gravity affects the motion of stars you can see with your naked eyes. Others sit at the centers of galaxies, billions of light years away, their existence revealed only through the light of matter dying in their accretion disks. And still others may be drifting through the solar neighborhood, primordial remnants from the Big Bang, undetectable except through their gravitational influence on passing stars. Every terrifying type of black hole has been explained. The cosmic taxonomy is complete. The gravitational predators have been cataloged and classified. But the fundamental mystery remains. Why does the universe permit such objects to exist? Why do the laws of physics allow matter to collapse so completely that it vanishes from reality? And what does the existence of black holes tell us about the ultimate fate of everything, including ourselves? There are no comforting answers. Only the mathematics of Einstein's equations, predicting with geometric precision that when enough mass gathers in a small enough volume, space-time must collapse into a singularity clothed by an event horizon. The universe did not ask our permission before creating black holes. It simply followed its own laws, consequences be damned. And those consequences include regions of space where causality ends, where time stops having meaning, where the future exists only as a path to oblivion. This is the cosmos we inhabit, a universe that manufactures gravitational execution chambers by the billions. A reality that permits, even encourages, the formation of structures that destroy information and break the laws of physics. A system that guarantees every massive star will eventually become a black hole, and every black hole will eventually evaporate into nothing, leaving behind only radiation and the memory of everything it consumed. If this exploration into the heart of cosmic darkness has left you unsettled, good. You should be unsettled. You are floating on a rock through a universe filled with invisible predators, any one of which could tear you apart atom by atom if you ventured too close. The fact that you exist at all is a statistical accident, a brief moment of organized complexity, in a cosmos trending inexorably toward maximum entropy and heat death. Hit that like button if you enjoyed staring into the abyss. Subscribe to this channel if you want to continue exploring the mechanisms by which the universe destroys itself. And remember, somewhere out there, a black hole is forming right now, another wound opening in the fabric of space-time. Another execution chamber ready to swallow everything that falls within its reach. The universe is not your friend. It is a machine for creating oblivion. And black holes are its most perfect invention,